Hi, hello everybody, my name is David aka The Blue, and today we're asked to use the divergence theorem to compute the flux of the field right there, which I'm going to call the vector field of F, since I don't want to say all that. But before we begin, I just want to say if I mess up my words or if I explain things not that well, that's because I just finished this class a couple days ago, actually like 2 weeks ago. So might not be the best at explaining this stuff, but I'll still try my best to help out with these types of problems. So let's begin. And just to recap, this is the divergence theorem here. I'm not going to read the entire thing, but basically all this tells us is if we hit these conditions, then we can compute the flux of the vector field by solving for the triple integral over the region E of divergence f dv. And just as a reminder here, this is how you solve for divergence of a vector field. So let's begin. And try not to get scared when seeing this, okay? And I'll go more into detail here, but when solving for divergence F, we're just going to be, solving for the dot product of these partial derivatives and your vector field. So for the first one, it's partial of x, and here, and since there's no oh, I just realized I have a white marker, so you can't see what I'm like doing there. But since there's no x here, our partial derivative is just going to be 0, since it's going to treat that as a constant. So here it's going to be 0. The same thing over here at the end. It's going to be the partial derivative of z, and since there's no z here, it's just going to treat this as a constant. But this middle part, this is what may look scary. But let's just take a moment and break this apart. This right here, there's no y here, so we can just treat this as a constant. And even though there's a y here, the bottom part is just, again, another constant. So all we really need to do is remember the derivative of arctan of u, or like arctan of a variable right here. And I wrote it down here for us to remember. So we can write this as 1 over x squared plus c squared, and let's not forget the square root, times the derivative of arctan of u, where u is just y over the square root of x squared plus c squared. So this is going to be 1 over 1 plus y over the square root of x squared plus c squared times u prime, which, since we only have y, the prime, we're doing a partial derivative of y, that's going to be 1 over the square root of x squared plus c squared. And we got that done. All we need to do is just simplify that here, but let's not forget that we got that 0 from the partial derivative of z over here. So let's simplify this a bit more. We recognize that this is just 1 over x squared plus c squared, sorry, the square root of that squared. So we can rewrite that as, and let me just get rid of this here so I have more space for myself, as 1 over x squared plus c squared times, and then this bottom part is also going to be squared, so we can simplify this as well as 1 over 1 plus y squared over x squared plus c squared. Didn't really need to put parentheses there, I just wanted to do that. And then this is where we're going to manipulate our function here a little bit. We can rewrite 1 as x squared plus c squared over x squared plus c squared, because this is equal to 1. So when we add this down here, 1 over x squared plus c squared, x squared plus c squared over x squared plus c squared plus y squared over x squared plus c squared, these just have the exact same denominator, so we can combine those into 1 over, and my bad if that's a little messy, I just wanted to do that really fast, x squared plus c squared. And then this we can simplify even more by just getting the reciprocal of that, and it will turn into 1 over x squared plus c squared times x squared plus c squared over x squared plus c squared plus y squared, which I will rewrite as x squared plus y squared plus c squared since that's in proper form. But that just cancels out right there, and this is just 1 over x squared plus y squared plus c squared right here. And this is equal to divergence of a vector field f, because remember, the partial derivative with respect to x of this is just 0, and the partial derivative with respect to z of this is just 0 as well. So we're only getting the partial derivative of the middle portion right there. And this, we just barely found out what divergence f was. We still need to compute the integral. There we go. I made it smaller and I just brought it to the side so I can write our integral here. Let's remind ourselves that our region E lies between the spheres x squared plus y squared plus c squared is equal to 1. X squared plus y squared plus c squared is equal to 25, and the first octant. The first octant just means that our coordinate values x will be greater than 0, y will be greater than 0, and z will be greater than 0 as well. So we'll use that later, but let's realize that to make this easier on us, we can just transform our rectangular coordinates into spherical coordinates. So let's remind ourselves that rho squared is equal to x squared plus y squared plus c squared, which in this first sphere, that's just going to be 1, which means rho is equal to 1. And for this other sphere, rho squared is going to equal to 25, which means rho is equal to 5. And using the fact that we're in the first octant, we can visualize and understand that the boundaries for phi and theta will be 0, phi, and pi over 2, 0 theta, pi over 2. And the reason that is because this satisfies our condition right here of the first octant. So now we know our limits of integration. We can actually put it all together, set up our integral, and solve for the flux of the field. My apologies. So yeah, we have 0 to pi over 2, from 0 to pi over 2, of 1 to 5, and I forgot to do one thing. This right here, we can change this into 1 rho squared, because again, this is just x squared plus y squared plus c squared, which is rho squared. And let's not forget about our Jacobian. When switching over to spherical coordinates, we're going to have rho squared times sine of phi. And since we're going to be multiplying this times rho squared sine phi d rho d phi d theta, we can recognize that that just cancels itself out. So we are actually going to be solving a much more simpler integral. So there's no need to panic anymore. We got all the hard stuff done. Now we can actually solve this. So this will be 0 to pi over 2, 0 to pi over 2, from 1 to 5, of sine of phi d rho d phi d theta, and this is just going to be 0 to pi over 2, 0 to pi over 2, of rho sine phi from 1 to 5 of d rho d theta, which is just 5 sine phi minus sine phi d theta, which is just going to be 4 sine phi. And I'm actually going to take that coefficient of 4 outside of the integral. So this is going to be 4, 0 to pi over 2, from 0 to pi over 2, of sine phi d theta, which this is going to be negative cos of phi from 0 to pi over 2, which cos of pi over 2 is just 0, and cos of 0 is just 1. So we're going to get negative 0, which is a 0, minus negative 1, which is just going to be positive 1. So this would be 4 times the integral from 0 to pi over 2 of 1 d theta, which will just be 4 theta from 0 to pi over 2. And pi over 2 minus 0 is just pi over 2. So this is going to be 4 times pi over 2, which in the end is just 2 pi, and that is our answer. Yeah, it's a lot of work, but it's really fun, and honestly, this is one of one of my favorites just in this class. I got a lot of favorites here, but yeah, hope you guys enjoyed it and this helped out to understand, even if like I may not have conveyed things as well. But yeah, I'll see you guys next time. Goodbye.